Pluto is a distant, dim, and relatively small astronomical object that was once considered a full-fledged planet in our solar system. However, recent and surprising statements from leading space experts like Neil deGrasse Tyson and Mayoka have thrust Pluto back into the spotlight with a startling claim that this icy world could potentially be on a collision course with Neptune. According to them, this is not just speculation but a genuine warning of a possible catastrophic encounter. The idea seems almost unbelievable, yet if Pluto's orbit were to shift even slightly, it could bring about a devastating planetary accident. This raises unsettling questions. Could Earth also be at risk? And how could such an extraordinary cosmic event unfold? To understand this possibility, one must examine Pluto's peculiar orbit. Unlike the near-circular paths of most planets, Pluto follows a highly elongated and tilted trajectory, inclined by about 17 degrees compared to the Sun's plane. It takes Pluto an astonishing 248 Earth years to complete a single revolution, and since its discovery in 1930, it hasn't even finished one full orbit. Its unusual path brings it perilously close to Neptune's orbit, which explains the growing concern. Renowned astronomers such as Neil deGrasse Tyson and Michiyaka warn that this irregular orbit could, under the right circumstances, lead to a dangerous interaction between the two celestial bodies, an event that might reshape not only our understanding of planetary dynamics, but also raise profound questions about potential risks to Earth. One of the most fascinating aspects of Pluto's orbital path is that it actually intersects Neptune's orbit. For about 20 years during each orbital cycle, Pluto moves closer to the Sun than Neptune does, defying what we might expect from their usual positions. This naturally raises the question, why haven't the two bodies collided? The answer lies in the subtle gravitational effects of nearby celestial giants and the intricate balance of orbital mechanics. Ever since Pluto's discovery, astronomers have studied its unusual path, noting that unlike most planets which follow nearly circular loops aligned with the Sun's plane, Pluto's orbit is highly tilted and irregular. The puzzle deepened when it was realized that Pluto's trajectory crosses Neptune's, yet both bodies remain stable. This stability highlights the complexities of space dynamics, particularly the three-body problem, the challenge of predicting how three celestial objects, like Pluto, Neptune, and the Sun, interact through gravity. In Pluto's case, the interplay of its elongated path, Neptune's orbit, and the Sun's pull create an interlinked system that prevents chaos. Astrophysicists point to mechanisms such as asynchronous oscillation, orbital drift, and what's called the VZK wobble as key to maintaining this stability. Specifically, asynchronous oscillation ensures that even though Pluto's orbit intersects Neptune's, the two bodies are never in the same place at the same time, allowing them to coexist without collision. When Pluto passes through the region of Neptune's orbital path, it is always positioned at least 90 degrees away from Neptune, providing a safe angular buffer that prevents a direct collision. Another safeguard comes from orbital drift, which refers to the vertical displacement of a body as it moves around the Sun. In Pluto's case, this means that when it approaches Neptune or another massive planet, it is usually far above or below their orbital plane, further reducing the chances of an impact. An additional stabilizing factor is the VZK wobble, named after researchers Zell, Kai, and Kaku, who investigated the gravitational interactions of celestial objects. This concept explains how three massive entities, Pluto, Neptune, and the Sun, affect each other's motion. Although Pluto's orbit may seem erratic, the wobble ensures a long-term stability, keeping the dwarf planet on a steady path and preventing chaotic deviations or dangerous encounters. This three-body dynamic highlights the balance within orbital mechanics and offers insight not only into Pluto's motion but also into the larger workings of planetary systems and even distant galaxies. Computational models developed in the 1980s suggested that while Pluto's orbit benefits from these stabilizing mechanisms, it still carries a degree of unpredictability, where small variations in initial conditions could cause significant deviations over centuries. Despite this, Pluto has remained remarkably steady over long timescales. Modern data has further revealed how the combined gravitational forces of Neptune, Jupiter, and Saturn shape Pluto's trajectory. Pluto and Neptune, for instance, share a unique orbital resonance. For every 2 laps Pluto completes, Neptune makes 3, ensuring they never occupy the same region at the same time. Beyond Neptune, Jupiter's immense gravitational pull plays a major role in preserving Pluto's path, while Saturn also contributes to this delicate balance. Studies indicate that Jupiter's influence alone may help maintain Pluto's stability for billions of years. Together, Neptune, Jupiter, and Saturn act as cosmic guardians, ensuring that Pluto continues its safe, if unusual, journey through the solar system. The stability of our solar system relies on delicate gravitational balances, without which space would be far more chaotic. Objects like Pluto could easily crash into other bodies or be expelled entirely, sparking chain reactions that ripple across the cosmos. This is why understanding Pluto's movement, particularly its potential encounters with Neptune, is so vital. Its case demonstrates how even seemingly unstable orbits can achieve harmony through intricate gravitational and kinetic interactions. At the same time, it highlights the need for continuous observation and analysis of such anomalies to better grasp our place in the universe. Pluto's orbit, with its irregularity and unpredictability, is a striking example of orbital chaos, the sensitivity of celestial paths to even the smallest changes in initial conditions. For Pluto, tiny shifts in speed or position could, over time, produce dramatic differences in its trajectory. Computer simulations have been invaluable in studying this behavior, allowing scientists to model gravitational interactions with planets like Neptune and test how slight adjustments might alter outcomes. As early as the 1980s, digital models revealed that despite stabilizing mechanisms such as asynchronous oscillation and orbital drift, Pluto's orbit still contained elements of unpredictability. A minuscule difference in its starting position or velocity could generate vastly different results in a short period. Yet remarkably, Pluto's path has remained steady for billions of years, suggesting an underlying consistency hidden within its apparent chaos. Predicting the motions of celestial objects with irregular orbits remains a challenge, as even advanced mathematical models depend heavily on precise starting values, and small errors can lead to wildly divergent outcomes. Still, studying Pluto's relationship with massive planets deepens our understanding of solar system dynamics, showing how each planet's mass and position exerts influence over others. This complexity is why some astrophysicists, including Neil deGrasse Tyson, have raised concerns about a potential Pluto-Neptune collision. While Pluto's orbit has long appeared stable, Tyson warns that even minor changes could one day destabilize the balance, leading to catastrophic consequences, though not in the immediate future. For him, Pluto's reclassification as a dwarf planet reflects evolving science rather than disrespect, but its overlapping orbit with Neptune underscores the universe's fragility. Alongside physicist Makioku, he stresses the need for constant vigilance in studying orbital dynamics. Together, they remind us that while humanity has achieved much in astronomy, the cosmos still holds countless mysteries, and Pluto's peculiar journey stands as a symbol of both its hidden dangers and its profound beauty.